Hey there, fellow AI aficionados. As we keep pushing these LLMs to be better at following our instructions, like more and more complex instructions, it really makes you wonder, can they even tell when they've messed up? Like when they've misunderstood our instructions?
It's a question I think about a lot, especially as we're asking these models to take on these really complicated tasks. Knowing if they can self-evaluate, that's critical.
Yeah, no doubt. And thankfully, there are some seriously sharp people working on this. Today, we're diving deep into a new paper. It's by Heo, Xiong, Heinz Demel, and Narain, and it's hot off the ArcSIF preprint server. They're tackling uncertainty estimation in instruction following LLMs.
One of the things that really grabbed me about this paper is how it highlights kind of a key distinction.
Yeah.
They're saying that just looking at how factually accurate an LLM is, it's not enough to know if it really truly understood and followed the instructions.
Right. Like you could be a whiz at rattling off baseball stats, but still not know how to hit a curveball. So how do these researchers propose we should be thinking about and measuring uncertainty in this instruction following context?
Okay, so they actually get into the weeds here, like really dig into the nuances of all the different approaches. For example, they talk about semantic entropy, which is, it's a pretty useful metric for uncertainty in, say, factual tasks. But they show that when you try to apply it to instruction following, it can be, well, kind of misleading.
Gotcha. Can you give us an example?
For sure. So let's say your instruction is, give me some benefits of regular exercise. Now imagine one LLM responds with, regular exercise strengthens muscles. Another says, regular exercise reduces stress.
Okay, both totally true statements.
Exactly. Factually accurate, right. And they both follow the instructions. But here's the thing. The paper points out that semantic entropy, it might actually flag high uncertainty here just because those responses have different meanings, even though they're technically both following the instructions.
Huh. That's really interesting. So if we rely on these kind of traditional methods, we might get a warped view of how well an LLM is actually doing with instruction following. So what did these researchers actually do to, address this challenge?
Well, they rolled up their sleeves and got to work analyzing a whole bunch of popular LLMs, different sizes, architectures, you name it. And to make sure things were super rigorous, they used the IFEVL benchmark, which, if you don't know, is specifically designed to test instruction following in a really standardized way.
Okay, smart move. A benchmark like that, it helps keep everything consistent, provides a more objective way to evaluate, right?
Absolutely. And get this, it gets even more clever. They actually brought in GPT-4 to help them filter out any low-quality responses in their analysis.
Whoa, using one LLM to, grade the others?
Yeah.
That's next level, but why even go to all that trouble?
Because they wanted to be absolutely positive that any uncertainty they were measuring was truly about the LLM's instruction following ability, and not just some quirk of the test itself. It's a really, really elegant way to isolate the exact variable they're interested in.
So they've got their lineup of LLMs, this super robust benchmark, and they're even using GPT-4 for quality control, like some kind of AI teaching assistant.
Yeah.
What'd they find? Were any of these LLMs actually able to, judge their own instruction following skills?
Okay, so get this. In some of the simpler tasks, the LLMs actually did a pretty decent job of self-evaluating.
Yeah.
They used this method called verbalized confidence. Basically, the LLM gives itself a score on how well it thinks it followed the instructions.
Wait, hold on. So we're just straight up asking the LLM, hey, how confident are you that you nailed that instruction?
Pretty much. It's wild, right? Like they've got this little internal critic just sizing up their own performance. And the thing is, in those less complex scenarios, it worked, surprisingly well, but...
There's always a but,
Yeah.
especially in cutting-edge AI research.
Right. So the paper, it actually says, in more challenging scenarios, even the LLM's internal representations struggle to accurately estimate uncertainty.
Okay, hold up a sec. Internal representations. Are you saying we can, peek inside the LLM's neural network and get a glimpse of what it's, thinking?
That's exactly what I'm saying. They use a technique called linear probing. Imagine, having this tool that lets you examine different layers of the LLM's, I guess you could say its brain, kind of like a neuroscientist probing different parts of the cortex.
Okay, I think I'm getting the picture.
Hmm.
So what they find in those deeper layers, those internal representations?
Get this, those internal layers, they're packed with information about uncertainty. It's like the LLM, it kind of knows when things feel a bit shaky, even if it can't always, articulate it clearly in its output.
So they're aware of the uncertainty on some level, but they're not so great at expressing it.
Exactly. And to really dig into this whole thing, the researchers, they categorized the tasks by difficulty. And for the simpler tasks, the ones they called control easy in the study, the LLM's self-evaluation, using that verbalized confidence thing and normalized p true, those were actually more accurate than the traditional, like, logic-based measures.
Okay, whoa, whoa, whoa. Too many technical terms at once for me. Normalize P true. What even is that?
Oh, sure. Sorry about that. Okay, imagine you've got an LLM generating a bunch of different responses to a single instruction, right? Normalized p true basically calculates the probability that the LLM will get that instruction right based on all those different responses. So it's basically like gauging its confidence level.
So for the easier tasks, the LLMs were better at just saying, yep, nailed it, or, not so sure about this one, than relying on all those complex calculations, those internal probabilities.
Yeah, basically. It seems like for those easier tests, at least, the more like intuitive self-evaluation methods, they lined up better with their actual performance. But of course, as you can imagine, things got a lot more interesting when they started looking at the really hard stuff.
Okay, so for those easier tasks, the LLMs had a decent handle on how well they were doing, which is pretty wild. But what about those tougher instructions, the ones that really make you sweat? Did their self-evaluation skills still hold up?
That's the million-dollar question, isn't it? And, well, it turns out there's no easy answer. The findings for those more complex tasks, they were all over the place, really. Like, sometimes the traditional logic-based methods were better at predicting uncertainty, but then other times the LLM's own self-evaluation methods, those were actually more accurate. It seemed to depend a lot on the specific model and, the architecture they were using.
So no clear winner when it comes to measuring uncertainty in these more challenging scenarios.
Not yet, anyway. And maybe the most important takeaway from all this is, well, none of the methods, not a single one, not even the ones looking at those internal representations, they were really great at predicting uncertainty. When the LLM made, those subtle errors, the responses that are like almost right, but they miss some crucial detail or they just slightly misinterpret what the instructions are asking for.
So even though we can see some awareness of uncertainty in those internal signals, they haven't quite figured out how to use that information when it really counts, those more nuanced situations.
Yeah, it's like they know something feels off, but they can't quite put their finger on what it is, And that, I think, is a really, really important area for future research to focus on. And in fact, the paper actually emphasizes this point. They say this inability to really accurately estimate uncertainty in those really complex scenarios. It points to inherent limitations in LLM's ability to handle complex uncertainty.
So where do we go from here? Even if those internal representations aren't the be-all and end-all, how do we even start to build more reliable uncertainty estimation methods for these really advanced instruction-following tasks?
Well, the researchers, they suggest that we might need to move beyond, just asking the LLM how confident it is, or just relying on those internal probabilities. Instead, we might need to develop like more sophisticated methods for decoding what those internal representations are actually telling us. Help the LLMs, express their uncertainty more clearly, especially in those tricky edge cases.
It's like we need to develop a whole new language for understanding what the LLM is trying to tell us, even when it can't quite say it directly.
Exactly. And the potential here, it's huge. Just imagine, a future where LLMs, they don't just blindly follow instructions, but they can actually explain their reasoning, they can flag potential errors, even adapt their behavior, based on their own internal sense of uncertainty.
Now that is a future I'm excited to be a part of. And for all of you AI engineers and researchers out there listening, this paper is a must-read. It's not just about the challenges, but it's also like a roadmap. It's a roadmap to a future where AI is more reliable, more transparent. Until next time, keep asking the tough questions, keep pushing those boundaries, and remember, the journey of discovery is just as exciting as the destination itself.